Okay. So in this session, we will consider an example for force current analogous circuit. Okay. Force current or FI analogy. So that is for a given mechanical system, how to obtain force voltage, force current analogous circuit. So consider the given system. So it has a spring K and there is a mass M and a force F of T is applied, and the mass is getting displaced by x of t, and also the friction element is P. So this is a given mechanical system. So for this we have to write now force current analogous circuit. So first step will be we have to write the equivalent mechanical system. Equivalent system. So in the equivalent mechanical system, so there is one displacement. So there is only one displacement. So therefore this corresponds to one node. One node. So first mark the node x of t. So now spring mass as well as B. Okay, so they are connected in parallel because they all come under the influence of this displacement. Okay, so then K, and then we have the friction element. This is B. So next the applied force F of T. F of T. So the same equivalent mechanical system even we draw in case of force voltage analogous circuit also. So here the only difference will be when we start writing the equations for particular analogous circuit. Okay, that is as it is a force current analogous circuits. Now we have to substitute force analogous components in the differential equation. Okay, so therefore now it may be a force voltage analogy or force current analogy, or even torque voltage or torque current analogy. First we have to write an equivalent mechanical system. So after this step, so next we will write the differential equation. So here you can see that as there is a single node, so we have one differential equation showing the characteristics of this particular system. So therefore the differential equation will be f of t, applied force f of t will be equal to m into d square by dt square of x of t plus b into dx by dt plus k into x. K into x. Now after writing this differential equations, now we have to take the Laplace transform. Then it becomes f of s equal to m into, for second order, that is d square by dt square, we have s square into x of s plus b into, b acts as a constant now. For d by dt it is s. For x of t, okay, so here I can write x of t, s into x of s plus last component k into x of s. Okay, so now still you can take that x of s as a common term. So x of s into m s square plus b into s plus k. So this is our equation for the given system in Laplace transformed version. Okay, even in FV voltage analogy also you are writing the same equation. So now in the third step, okay, so in the third step we are going for FI analogy. That is, we have to substitute FI analogous components in equation 2. Now in FI analogy, f of s is analogous to the current source. In FV analogy, f of s was analogous to voltage source V of s. Now it is analogous to current source I of s. Okay, so because we have two electrical circuits, one is series LCR circuit, other one is a parallel LCR circuit where current source is the input. Next, in the mechanical system, we have x of s, that is displacement. This will be analogous to phi of s. And next, whatever this mass is there, this will be analogous to c. Similarly, the friction component, that is B, will be analogous to 1 by R, and last spring will be analogous to 1 by L. So now we have to substitute these many terms in equation 2, and then we have to rewrite equation 2 using this particular analogy. Okay. So therefore, rewriting equation 2 using FI analogy, we have the next equation, phi of s is equal to, um, just a minute, it is not phi of s, it will be I of s. Okay. So this will be I of s. I of s will be equal to, first we have to write phi of s, okay, because we are replacing individual terms. So phi of s into cs square plus 1 by r into s plus 1 by l. Okay, so earlier what was the basic equation? F of s equal to x of s into m square plus b into s plus k. Now we have replaced all the terms and this is the equation we have. Now the term phi of s has to be replaced by voltage. Okay, so because we are writing the final analogous circuit on node basis where we have to represent the node voltage. Okay, so therefore we have to replace phi of s. So how to replace this? So we know the relation V of t is nothing but d phi by dt, rate of change of the flux. Okay, so taking the Laplace transform on this, V of s is equal to s into phi of s, or V of s by s is equal to phi of s. Okay, so therefore now we have got the voltage component. Therefore, we will replace phi of s by V of s by s in this equation. Therefore, now rewriting I of s, it will be equal to V of s by s into c s square plus 1 by r into s plus 1 by l. Okay, so now this is a new equation we have by including this V component, voltage component. Okay, so now we will further simplify this. That is, we will multiply V of s by s with the individual terms. Therefore, I of s is equal to, so now one s term gets cancelled. So is a c is a constant term. So we have here s into V of s for the first term, plus second term s gets cancelled. We have simply V of s by r, plus in the last term there is no cancellation, but here 1 by L is a constant term. So therefore we will write 1 by S into V of S as it is. Okay. So now this equation is ready to take the inverse Laplace transform. So now take inverse Laplace transform of the above equation. Okay. So for taking the inverse Laplace transform, what we have? For S, we have to write d by dt, and for 1 by s we have to replace by integral dt. Okay, so therefore I of s will be written as I of t, because now we are coming back again to the t domain. So I of t is equal to c into, so now for s we have to substitute d by dt. V of s will be now written as v of t. because it is the inverse transform, plus now it is 1 by r into, for v of s it is simply v of t, plus 1 by l. Here for 1 by s you have to substitute integral of, okay, integral of v of t into dt. Okay, so for v of s it is v of t. Now this is what is the final equation which will be used to draw the Fi analogous circuit. Okay, so therefore let us see now how to draw the analogous circuit. Okay, so I'll rewrite the final equation. Final equation, I of t will be equal to what we had, c into d by dt of v of t plus 1 by r into v of t plus 1 by l into integral v of t into dt. So this was the previous equation that we derived. So now to draw the Fi analogous circuit, okay, it is written on the node basis. So therefore, which is the node voltage here? Okay, so v of t, v of t, v of t, the three terms. Okay, so this acts as a node voltage, and as there was only one displacement in the given mechanical system, now we have a single node v of t. Okay, so to this node we have to connect the source I of t as well as to the same node. So you can see that d by dt of v of t. Okay, so to the same node we have to connect the capacitor C. This is also 1 by r into v of t. So therefore the resistor is also connected to the same node. And last one, this inductor is also connected to same node v of t into dt. Okay, so this is called as the Fi analogous circuit. Fi analogous circuit. Okay, so we have the individual term comparison with the mechanical system. So in the mechanical system we have what, in place of I of t the force f of t was there. Okay, in mechanical system there was one displacement x of t. So now we have in electrical circuit one node voltage v of t. Similarly, there was one mass, now it has become a capacitor. There was one friction, now here we have in the circuit one resistor, and there was uh, uh, one spring. Okay, and now we have one inductor in the Fi analogous circuit. So like this, so individual components are replaced and a Fi analogous circuit can be obtained. So this is one example. So let us take a similar